Okay, our next speaker is Michel Goemans. Michel holds the Layton Family Chair at the Department of Mathematics at MIT. He is known for his contribution to approximation algorithms and in particular for the use of semi-definite programming and the primal dual method in the design and analysis of algorithms. He has received a number of prizes, including the Falkenstein Prize given to an outstanding contribution in discrete mathematics and the Farkas Prize for a mid-career optimization researcher. There are a few more which I will not list. Today he will talk about a joint result with Thomas Rothfuss, for which they got a Best Paper Award at the recent SODA.
Okay, thank you, Ziv, and thank you for the organizers for inviting me. Unfortunately, I will not follow the trend of previous invited speakers. So let me try to find the talk. So, okay, so I would like to talk about bin packing. And the result is joined with Thomas Rothfuss, who was a postdoc at MIT and is now on the faculty at the University of Washington. So the bin packing problem is a very simple problem. We are given a bunch of items and of sizes S1 up to SD, but we have several items of the same size. So for each item, we are given also a multiplicity, A1 up to AD. And the goal is to pack items into a minimum number of bins of size 1. So often the problem is stated with multiplicity 1, but we're looking at the variant which is sometimes called the 1D cutting stock problem, in which the multiplicity of every item is given, and it's given in binary. So for example, we have 3 items in this case, the red, green, and purple item. And we can, for example, decide, so we have a bunch of bins, we can decide to put the red items in the following way, in the different bins, and the green items in that way, and the purple items in this way. So we get a packing of a certain number of bins, and the goal is to minimize the number of bins. So the problem, even if every item has multiplicity 1, if the sum of the sizes is equal to 2, it's NP hard to distinguish between the use of just 2 bins and whether you need 3 bins. So that comes from exact partition. And in all cases, there is an additional difficulty because of this high multiplicity encoding. So given that the multiplicities are encoded in binary, the input size is really depends on the log of these A sub i's and not on the A sub i's. And so to be polynomial, we need to be polynomial in D, in the log of the A sub i's, and also in the, let's say, the largest denominator delta in the input size, in the sizes of the items. And so, I mean, this is completely trivial, but if you had only 1 item and with multiplicity A1, you need A1 bins. I mean, if let's say, if S1 is more than half, you need A1 bins, but that's exponential. So the number of bins may be exponential in the number of in the input size. And so what you need to do is you need to give a compact representation of the output. So so the question, one basic question is, how many patterns do you need to represent the output? And so there is a nice result of Eisenbrand and Schmonin. I'll give the proof because it's extremely simple. That shows that there exist optimum packings in which you have at most 2 to the D bin patterns. And also there exist packings in which the number of bin patterns is at most the sum of the log of the A sub I. So the second bound is polynomial in the input size. And so even this high multiplicity encoding of bin packing is in NP. So in general, here is what is known in terms of solving the bin packing problem. Now, in terms of approximation algorithm, it started in the 70s with David Johnson, who showed, for example, that force fit decreasing gives an approximation guarantee of 11/9 of the optimum plus a constant term. Then in the early 80s, there was a asymptotic FP task that was given, so in which you get within 1 plus epsilon of the optimum plus an additional number of bins that depends on epsilon. And then the best results known are by Karmaker and Karp, and then recently improved by Rosvos. So Karmaker and Karp shows that you can get a number of bins, which is the optimum plus an additive guarantee of log squared d. So log being d again is the number of items, and it's and Rosvos improved it to log d, log d. So for constant d, it was known, up to this point, it was known that its polynomial for d is equal to 2. So if you have only 2 items with multiplicities, it was known to be polynomial, and I'll show you how you can do that easily. And it was also known that you can get within 1 unit of optimum in time that's polynomial for fixed d. So it's W exponential in d and times a polynomial term. And the question was even whether you can do it in polynomial time for d is equal to 3. And so what we'll show is that for any constant d, we can solve it in polynomial time. And the proof is geometric and fairly simple, so I will give you all the ingredients in the proof. D is the number of items. So we have n items. We have not n items. We have d items, but each item comes with a multiplicity. The number of types, exactly. So the number of items is the sum of the A sub i's from I1 to D. But D is the number of item types, yes. So here is a geometric view which will be central to our algorithm. Is suppose you consider the vector of sizes. So that's the vector S. And suppose you look at all possible patterns for one bin. So you look at the x's such that S transpose X is at most 1. So that tells you how many items of item type 1 you can use, how many items of item type 2 you can use in the same bin. And so all the integer points in P represent the feasible patterns. And A is the given multiplicity, and so the goal is to find a bunch of integer points in P and give multiplicities of them so that you can get the point A. So the problem is, one problem is that you may have exponentially in the input size, many points in P, many integer points in P. And so one question is whether we can find a small number of patterns we can use, and then we have to also talk about the weights that we can use on these patterns. So it will be so one classical way to approach bin packing, for example, to approximate it, is to use the configuration linear program that was introduced about 50 years ago by Gilmore and Gomery. And so the linear program is so first let me write an integer program. So you have a variable lambda x, which is for every x in P intersect ZD. So for every feasible integer pattern, you have a variable lambda x. And then what you'd like is lambda x represents the number of times you use that specific pattern from the bin. So you'd like that the sum of lambda x times x is equal to a. And that's the integer program, so that's the bin packing problem. And you can relax it to looking at the lambda x which are non-negative. And so the best approximation algorithm of Karmaka and Kamp and also of Rosvos use this configuration LP. So they show that you can solve it approximately in polynomial time, and then you can use it to get a good packing. Now, one thing that's not completely obvious is that for fixed D, you can solve this linear program in polynomial time. So, because again, for fixed D, remember that the number of points in P intersect ZD can be exponential in the input size. So the number of variables is exponential, and so still we need to argue that you can solve it in polynomial time. So it can be done in several ways. One way is to take the dual of that linear program and then to use the ellipsoid algorithm and to solve the separation in polynomial time, the separation being a knapsack problem in this case. Another option is to actually to look at P intersect ZD and so look at the vertices of that convex hull, and one can show that the number of vertices is going to be polynomial. So even though the number of integer points within P can be exponential in the input size, the number of vertices of the convex hull will be polynomially bounded. So, so let me just as a warm-up, even though that's not the technique that we will be using. So if you want to sleep for 5 minutes, that's okay. But I just want to show you that for D is equal to 2, it's very simple to solve the bin packing problem. And the idea is to solve that linear program and to round it. And that's going to be enough to solve the bin packing with 2 item types. So if you look back at the LP, you have A as dimension D, so you have D constraints. So you have D constraints. So if you look at an extreme point of the LP, it will have exactly two variables that are non-zero. And so you have only 2 bin patterns, let's say x1 and x2. So x1 represents what's in one bin, and x2 represents what's in another bin. And then you have some multipliers, lambda x1, lambda x2, which can be fractional. So the first thing is to take this lambda xi's and to take the floor of that, and you can open that many bins of each pattern. And then for the rest, you can look at, now that you have opened these bins, you can check how many items of both types are uncovered. And so that's going to be the fractional part of lambda x1, which is f1, times, so this should be, fi should be the fractional part of lambda xi, not xi. So it should be, so y is f1 times x1 plus f2 times x2. These are the number of items of type 1 and of type 2 that are uncovered. And you can just check if the LP was using between 1 and 2 additional bins, then you can just open 2 bins, one in which you'll have the pattern x1 and one in which you'll have a pattern x2, and that's going to be feasible, and it's going to be the number of bins used will just be the ceiling of the LP. But if f1 is at most 1, if f1 plus, and that should be f1 plus f2 is at most 1, then in that case, all the bins, all the items fit, all the remaining items fit in one bin, and so you can just open one more bin. So that's the case in which d is equal to 2, you can just solve the LP and round up, and that's going to give an optimum solution. Unfortunately, that's not true for 3 item types. So if you solve the LP, there can be a gap of more than 1 unit between the LP and the optimum. So we need to do it differently. So from now on, we won't be using that configuration LP, and instead we'll go back to the geometric view, and what we're going to do is the following. We're going to look at the we're going to look at a polytope P, and we're going to look at the integer points in P, so P intersects ZD, and we look at the integer cone. So what is the integer cone? It's the integer non-linear combination, non-negative combinations of these elements in P intersects ZD. So we look at this cone, and we'd like to decide whether that cone intersects a given polytope Q. So we're given 2 polytopes. We look at the integer cone defined by the integer points in P, and we'd like to know whether we get a point in Q. And that's the problem that we're going to solve, and we'll show that this is, can be done in polynomial time, and this can be for fixed D. So on running time will be something like, so the input length to the 2 to the 2D, roughly. So that's an illustration of the integer combinations. So from bin packing can be described in the following way, indeed, because we can take as my polytope P to be the feasible patterns, but then I add a 1, so I do it in dimension D plus 1 instead of D, so I have X and 1, so that I can just check if I can get the point A and opt. So opt would be the number of bins used, and A would be the number of each item, the number of items of each item type. And we can do binary search on opt, for example. So for the rest of this talk, I'll focus on proving this and show you how you can decide this in polynomial time. So, but first let me go back to the fact that bin packing is in NP. Again, I'm not going to use this result, but it's a very simple result to state, and so I'd like to. It's just a few lines, and it actually is useful in many other contexts. So, so if you have a set of integer points, and you look at the integer cone of it, then you can find a polynomial size subset of P such that A will also be in the integer cone of P prime. So even though P can be large, there exists a subset of P of polynomial size, namely it's bounded by the sum of the log of the A sub I plus 1, such that you can prove that A is in the integer cone of P prime. So let's see how you can do this. So suppose you look at ways of expressing A, and among all ways of expressing A as an integer conic combination of the X in P intersects ZD, suppose you take the one with minimum support. And let's define that support to be P prime. So our goal is to show that P prime is small, namely that P prime is of at most sum of the log of the A sub I plus 1. So notice that if I take any subset of P prime, and I look at the sum of the points in that subset, that's going to be between 0 and A, because the sum over everything is A. So it's going to be between 0 and A. And so if P prime is very large, there will be two sets that will give you the same sum, because the number of possible sums between 0 and A will be the product of the AI plus 1. And so if P prime is, if 2 to the cardinality of P prime is more than that, then there will be two subsets that give you the same sum, and then by the pigeonhole principle, and so you can reduce the support. So that was not the minimal support. So that's a simple way of showing that for bin packing, in which you have multiplicity, so for high multiplicity bin packing, that will be in NP. So that's not going to be, so this is not useful for us, because we'd like to show that when D is constant, we can even, instead of getting just a polynomial number of points P prime, we'd like just a constant number of points P prime. So here is a result of Eisenbrandt and Schmonin as well. So they show the following, that if you take any convex set and you look at the integer points within that convex set, then any integer conic combination can be expressed with at most 2 to the D points. And the proof is very, very simple. So what you do is suppose the support has more than 2 to the D points. So in that case, it means that there will be 2 points x and y that have the same support. So if they have the same support, the midpoint, the same parity, if they have the same parity. So if they have the same parity, then midpoint z will also be an integer point. And so what I can do is I can take some of the weight on x and y and move it to z. And so by a basic potential function argument, you can show that you improve, you get an improvement, and so that will stop when you have at most to the D points. So that's going to be useful. The problem is that we don't know which 2 to the D points to use. So so if we knew, we would be done at this point. So so one of the main tool that we'll be using is that we'll be using the fact that integer linear programming in fixed dimension can be solved in polynomial time. So that's a celebrated result of Lenstra back from the 80s. And so whenever you have in D dimension, so if x is in ZD, you can decide in polynomial time if AX is at most B as an integer solution. So in our case, it seems we are, I mean, to use this, we have a few obstacles to overcome. So we'd like to express A as a conic combination of points in P. The problem is that our variables are both the lambda x and the x. So this is not a linear program or an integer linear program, but it's a quadratic integer program. So what we need to do is somehow we have to show that this can be viewed to be linear. So the way that we're going to show that it can be viewed as a linear program is that we're going to show that some of the lambda x can be assumed to be 1, and so we'll fix them to 1. And we'll also show that for the ones that are not 1, we'll show that we can find them, we can guess them. And so either on some of the terms we'll fix lambda x, and on some of the other terms we'll fix x. Let me try to explain that in a few slides. So suppose I have a point x, an integer point in my polytope P, and suppose I have a parallelepiped that's inside P, and the vertices are integer points as well. So then what I can do is the following. I can look at, I can divide my parallelepiped into 2 to the d smaller parallelepipeds, and then I can check in which quadrant is x, and I can look at the corresponding vertex y, and I can look at the mirror image of y with respect to x. So that's z. And then what I can do is I can just decrease the weight on x and increase the weight on y and z. Now, when doing so, I can do that except if the weight on x is just 1. Because when I decrease the weight, I have to decrease it by a multiple of 2. So whenever the weight of x is only 1, I can do that. So this may leave lambda x with, so lambda x will either be 0 or 1. So if it is 0, fine, we can get rid of x. But if lambda x is 1, we have to keep x for now. But at the end, we get a bunch of points inside the parallelepiped that have weight 1. Plus, we use the vertices of the parallelepiped. Now, if the vertices inside, so the ones that have weight 1, if I have more than 2 to the d of them, I can do the same trick as before. I can look at the parity and still decrease it. So when you repeat this process, eventually we'll express, so we started from a point x, and so we're looking at a lambda x times x. So we had a multiple of x, and now we are viewing that multiple of x as a multiple of the vertices of that parallelepiped plus a bunch of points inside, but that have a weight of 1 now. So that's really nice because we had lambda xx, which was quadratic because we didn't know lambda x and we didn't know x. But now we look at, we know the vertices of pi, and so we are looking at an integer conic combination of the vertices of pi. So there we don't know the lambda x, but we know the points. And plus a bunch of points inside, but we have at most 2 to the d points, so d is fixed, so that's a constant. So we have a constant number of points inside that we don't know, but we know that they will be taken with a multiplicity of just 1. So their weight will be 1. So it seems that now we have kind of gotten rid of the quadratic term. So that seems to be useful. And so our goal is to, so that was for a parallelepiped. Our polytope is not a parallelepiped. So what we want to do is we want to cover the integer points within our polytope with polynomially many parallelepipeds. So for example, if you, in this, and again, we can do this for arbitrary polytopes. I've illustrated it for the kind of knapsack polytope that comes from bin packing, but we could do it from any polytope. So the claim is the following, that if you give me any polytope in fixed dimension, we can cover the integer points within it with polynomially many parallelepipeds. The parallelepipeds might not be of full dimension, that's okay. They might be of lower dimensions, that's not a problem. and all these parallelepipeds will have integer vertices. So, for example, this is a covering of all the integer points. So notice that the non-integer points are not necessarily covered, and also you see that one of the parallelepiped, the one on the bottom right, is not a full dimension, but that's okay. So that's what we want to do next. And so to do this, there are several ways of doing it. Here is one way. It's not going to give the best possible bound, but it's fine for a purpose. So what you do is you look at your polytope, which is given by AX is at most B, and you will split it into many cells. And the way you split it is you take any hyperplane that defines your polytope, and you look at translates of it. And by how much do you translate it? You translated it geometrically. So you take 1 plus 1 over d raised to some power, so 1 plus 1 over d to the k, for k taking integer values, and you move your hyperplane by that much. So you get a bunch of hyperplanes like this. You get polynomially many such hyperplanes, and you can look at one fixed dimension. So what will happen is that you'll have also polynomially many cells that are defined by, so you do that not just for one hyperplane, but you do for all the hyperplanes defining your polytope. And so you divide your polytope into two polynomially many cells. Now you look at each cell, and you look at the integer points within that cell. Now again, since we are in fixed dimension, you can show that the integer hull, so the convex hull of the integer points in that cell, will have polynomially many integer vertices. So that's Ci. So the green thing are the convex hull of the integer points in that cell. And now what we're going to do is we're going to get the parallelepipeds out of it. And for that, what we do is we take any simplex formed by the vertices. So in this case, I will take, since I'm in dimension 2, I will take 3 points, 3 vertices of Ci. And I will look at that simplex, and I will extend that simplex to a parallelepiped. Now, the nice thing is that why did I do the why did I go geometrically by 1 plus 1 over d to the k? The reason is that when you do that simplex, that parallelepiped, one can easily prove that that parallelepiped will still be completely within P. And so the nice thing is that that simplex is governed by a parallelepiped, and we do that for every simplex defined by d plus 1 vertices of Ci. So we have, if you do the calculations, what happens is that we have polynomially many cells. In each cell, we have polynomially many vertices of the integer hull. We take any d plus 1 such vertices. We look at the simplex. So we have polynomially many simplices. We get polynomially many parallelepipeds. And these parallelepipeds will cover all the integer points in the polytope. So we get polynomially many parallelepipeds in that way that cover all the integer points in the polytope. Now, when you do this, you get the input length to the, if you do the calculations, you'll see that you'll get the input length to the order d squared. You can do better, actually. I won't give the details, but you can, what you can do is, instead of looking at, we'll get a bit more, so the splitting into cells is a bit different. But then instead of looking at any simplex formed by d plus 1 vertices of Ci, what you do is you take the John's ellipsoid, which is the minimum volume ellipsoid that contains Ci, and that will have at most d square contact points. And you know that if you shrink it by a factor of square root of d, well, for that you need it to be centrally symmetric, but you can make it centrally symmetric first. Then you shrink it by a factor of square root of d, you know that you'll be inside Ci. So using that, I won't give the details, but you can reduce it. It's still polynomially many parallelepipeds, but now the exponent is in d and not d squared. So that's a small. I mean, it doesn't matter if d is constant, but it's the algorithm is not going to be practical. But this is maybe with d instead of d squared, maybe it's slightly more practical. So let me summarize what we have done so far and how we can solve these problems. So we have these two polytopes P and Q, and what we'd like to do is we'd like to decide if the integer cone defined by the points, the integer points in P, intersects Q or not. So what we'll do is we'll first take P and we'll find these polynomially many parallelepipeds covering P. So everything in the construction I showed, not only you get polynomially many parallelepipeds, but every operation can be done in polynomial time. So I haven't, you need to solve actually a bunch of, so for example, when you have a cell and you look at the convex cell of the integer points in it, for that you need to do linear programming, integer linear programming in fixed dimensions to be able to find these vertices. So we have to use Lensstra's algorithm a bunch of times to be able to construct these parallelepipeds, but everything can be done in polynomial time. Now that you have these parallelepipeds, we know that if there exists a conic integer combination of P that gives me Q, that gives me a point in Q, we know that it can involve at most 2 to the d points. So let me guess the 2 to the d parallelepipeds that contain these points. So that's again, d is constant, so 2 to the d is just a constant. So so in polynomial time, I can guess these 2 to the d parallelepipeds. Now that I have these 2 to the d parallelepipeds, I will just look at the vertices of these 2 to the d parallelepipeds. Each parallelepiped has 2 to the d vertices. So again, I have polynomially many vertices. I have a constant number of vertices of these parallelepipeds. I have 2 to the 2d, because I guess 2 to the d parallelepipeds, each having 2 to the d vertices. And so now I'm done, because I know that my set X, which are the vertices of these 2 to the d parallelepipeds that I have guessed, I know that I can use as variable lambda x, which is the number of times I have to use all these vertices. But I know the x. So x is not a variable. In the first term, the green x is not a variable. I know what x is. And then I have to add, for each parallelepiped, I have to add 2 to the d additional points, but with a multiplier of 1. And so over all the 2 to the d parallelepipeds that I have to guess, that's 2 to the 2d. So I get 2 to the 2d additional exabytes, which I don't know, but which are solutions to that integer program in P. So what happens is that I have an integer conic combination in Q that's now in which the things that are known form a linear function. So the lambda x in the first term are known, and the exabytes in the second term are known. So I can use Lenstra's algorithm now to find the lambda x and the exabytes. So let me recap. So for any polytope P, we can find a so there exists a polynomially so there exists a set X of integer points within P that can be computed in polynomial time, such that whenever A is in the integer, it's an integer combination, integer conic combination of these points in P intersect ZD, then I can express A as in the integer cone of 2 to the 2D points in X, and also 2 to the 2D additional points, but in which they have a coefficient of 1. So, so for example, X could be these green points, and then you get so you get that A can be expressed as a conic combination of these green points plus another 2 to the 2D points that we don't know. So, for bin packing, so this shows that in fixed dimension, we can for a fixed number of item types, we can do it in polynomial time. There are many variants of bin packing. So, for example, in the cutting stock problem, we have also not just one type of bin. So we don't have just a bin of size 1, but we have bins of different sizes, and each bin comes with a certain cost. And our goal is to find an assignment of the items to the bins so as to minimize the total cost of the opened bins. And so this can be easily fit in this framework as well. So you can view P now as the cross product of P sub i's of P sub j's, let's say, in which P sub j, the first D components represent what you can put in a bin of type j, and then the last item, the last entry represents the cost of that bin. So, but in fact, there are many problems that can be set up in the same with these polytopes P and Q. So, for example, there is a wide variety of high multiplicity scheduling problems that can be fit in this framework. So, for example, you might have in a scheduling problem your jobs with certain features or certain properties, and you might have many jobs that are identical. So you may have only a small number of job types, so maybe D job types, and each job type comes with certain release dates, deadlines, processing time, and also multiplicity. And then what you'd like to do is you'd like to schedule the jobs so as to, for example, minimize the number of used machines. So there are many variants here. I won't list them all, but in many cases, you can fit it by appropriately choosing P and appropriately choosing Q. You can actually fit it in this framework. So lots of high multiplicity scheduling problem can be solved now in polynomial time for fixed D, and that was also open. So it seems to have gone pretty fast, faster than I expected. Maybe I should have slowed down initially, but thank you for your attention. And
So
The yes. So so the so already the so the number of parallelepipeds is that we get is exponential in D, but then when we so that's going to be, so we'll have an integer linear program in roughly that many variables, and so Lenstra's algorithm will give you another exponential. So it's going to be doubly exponential in D.
So I guess any algorithm would be at least exponential in D.
Right. So
any guess of what's the correct answer, simply exponential?
It's a good question. We don't we don't quite know. So there is also there are possible improvements. For example, in the case, so I did everything for arbitrary polytopes P, but if you take the P that comes from bin packing, so that's a knapsack polytope, in that case, it's not completely clear if you really need to do the D point. So, so potentially there you could improve. So we know that for an arbitrary polytope, then you need 2 to the D, or D 2 to the, at least 2 to the constant times D. But for the knapsack polytope, we don't know if you need 2 to the D. So that could be potentially an improvement.
So you showed at the beginning that if you are ready to get additive D, then it's trivial.
Yes.
If you are ready to, but if you want to get like additive 1 or 2,
So
it's becoming much easier, or it's still?
So additive 1 is was known. So additive 1 was this result. So Janssen and Solesoba showed that you can get additive 1 in polynomial time times a factor that's doubly exponential in D. It's not trivial. So, but D is indeed trivial by the configuration LP and rounding. But from the configuration LP and rounding, essentially you get D and you cannot do much better than D. Potentially you could do a constant times D, but not, I mean a smaller than 1 constant times D, but not better than that.
So this holds even if D is not constant, just a little bit more than constant.
I believe so. I hope I haven't hidden any additional factors. There might be some factors that got lost in, not in translation, but in transition. Any other questions?